people there are. In principle, I don't mind, but if it becomes too many questions and then, we go off on a tangent.
Sure.
But
if it's too many, we will kindly ask to
postpone
to the end of the talk.
That's right. Yeah, maybe, Luca, you can have an eye on, I don't know whether people raise their hands because I may not look at it or not see.
Sure.
Okay. So, yes. Okay. So you're truly international here.
Yeah.
I think we will wait a couple minutes.
No problem.
It's still 2 to 5, 2 minutes.
Yes, still we have 1 minute before.
Well, in some places it's 2 to 11 in the evening, but it's okay.
Already 32 participants. It's much better.
By the way, could you please change the Moscow time in general announcement of our seminar, because still there is 7 p.m. but now it's in fact 6 p.m. Because
wait a second. Wait a second. It's written
maybe
5...
not now, but in principle, because
no. In my email, it's written 5 p.m. in Europe.
Yes, in your email everything
Moscow.
is fine. But in the main page of our conference, in program.
On the website, you mean?
On the website,
Okay,
yes, exactly.
Okay, I will see.
Not now, but in principle.
Yeah, I will see. It's a bit complicated. This time is changing everywhere differently. People even don't synchronize how they change clock around the world.
So now is a 41. Okay, yes.
That's increasing.
The title of the talk is amazing, Renata. I like it.
Yes.
Quantum gravity reloaded.
Yes.
I'm not sure how original this is. Other people have reloaded other things, like matrix. Yes. Wow.
Interesting that I translated your title in Russian. Then is give me in translation after quantum gravity a colon, two dot. Как бы двоеточие, two colon. Give me a colon. Give me a colon, yes.
Okay. So maybe it's not able to translate reloading.
No, it's okay. The translation is correct, but it's had some extra mark.
I hope it doesn't have it. I hope it doesn't have any military connotations that were not intended.
So now we are 46. I'm sure it will be 50 in a few minutes, but in any case, we have to start. Hello, everybody. Today we have a pleasure to listen the talk by Professor Renata Loll. She will tell us about quantum gravity reloaded. Please, Renata, 1 hour.
Yes, I'll do my best. So thank you so much, Luca, everyone who's here, for the invitation. I will give, it's a kind of overview and not super technical talk. I don't know exactly, what everyone's background is. So these two, can you see my cursor, by the way?
Yes.
Okay, yeah. So these two graphs are somewhat emblematic of the ideas I've been following. And also the time span from kind of the first 4-dimensional results we obtained in non-perturbative quantum gravity, which is here depicted by this lovely blob universe, to more recent, refined analysis where we are able to, for example, say something about curvature of the quantum universe. Anyway, so I'll get going by starting with, where do I come from? What is my perspective on quantum gravity? So my aim is here to construct a fundamental theory of quantum gravity, and that as a non-perturbative, diffeomorphism invariant quantum field theory of dynamical geometry. So almost, I mean, all of these words are important. I mean, non-perturbative is important, diffeomorphism invariant, which is closely related to background independent, the fact that it's just a quantum field theory, and that geometry is treated as generally dynamical. So, and of course, we want to understand what the physics is, so we will study its properties, and that will be a non-perturbative Planckian regime. So, as you are doubtless aware, this is difficult. So it presents technical, physical, and also conceptual challenges. So we have to deal with quantum field theoretic infinities, the absence of a fixed background space-time, which we of course use in standard relativistic quantum field theory. And we have to think about how to extract information from the theory, how to renormalize it in a way that respects the symmetries. Also, of course, to rederive a classical limit, and eventually we'd also like to make predictions of new phenomenology. So this is clearly a tall order. What I want to convey as my main message today is that major progress has been made on all of these points in the context of random geometry in the form of causal dynamical triangulations. So my definition is this is a minimal, non-perturbative quantum extension of general relativity. And it has already provided us with interesting results, namely on emergence of quantum spacetime, without putting it in by hand at all, from a kind of Planckian soup, you could say, of quantum geometric excitations. And it's also a blueprint for the type of results we can expect to obtain in such a non-perturbative formalism. So I would say it presents a fresh outlook on what quantum gravity is. Now, so why should you be interested? Well, number one, it's a kind of minimalist setting, and we're deriving interesting, new, and non-trivial results, despite the fact that we are only using kind of non-exotic and quite conservative ingredients, and of course, in particular, simply, quantum field theory. What is very important is that we have a functioning computational network framework, kind of our lab, and we can actually do computation and evaluate quantum observables which characterize quantum gravity beyond perturbation theory. The way you should think about it is that this methodology, so CDT, random geometry, is to gravity what lattice QCD is to non-abelian gauge theory, namely a tool that enables us to extract non-perturbative information, which we cannot currently do by any other means. So what's the second point about the demystification? It is about, the sentence by which virtually every popular article about quantum gravity starts. It says, oh, there is quantum theory, which is about the very small, and there is general relativity, which is about the very large, and they are fundamentally incompatible because, well, for example, they treat, time and space in a very different way. But of course, everyone who follows quantum gravity doesn't really take that attitude, but of course, we do believe that they are ultimately perfectly compatible. And indeed, kind of the only thing you have to take care of is, in my view, that you have to take care of the fact that geometry is dynamical. And that's a new thing. And if you do that, you can just stick to standard technology and concepts from quantum field theory and general relativity. So what is new here? One way of putting it is, look at general relativity. So the mathematical foundations of general relativity, of course, are those of Riemannian geometry, or more specifically pseudo-Riemannian, Lorentzian geometry. So these foundations were laid back in the mid-19th century by Riemann and others. Now, what we want to describe is quantum gravity beyond perturbation theory. And my claim is, well, it's just no longer adequate to simply rely on the good old, Riemannian geometry. We have to go further. And there is already names for how we should go further. It's mathematics of beyond classical Riemann geometry, and in particular, random geometry. And I'd like to quote this famous sentence from Riemann's thesis, habilitation thesis from 1854. So he, of course, in that thesis wrote down, the famous align element, ds squared is equal to g mu nu dx mu dx nu. So that's really kind of encapsulates the foundations of Riemannian geometry. But already in his thesis, he said, my considerations may not apply in the immeasurably small. And he said, there may be new physical considerations that will force us to go beyond. And I would claim we have reached this point where we have to actually go beyond, also in mathematical terms. Now, so why is what I'm saying also interesting, hopefully, or eventually from the point of view of phenomenology? I believe the most likely predictions we will be able to extract from the type of non-perturbative formulation I'm following will involve early universe physics, but not derived from kind of cosmology or quantum cosmology, but derived from the full quantum gravity theory without making any a priori symmetry assumptions. Okay, so here we go. And let's see, here I can advance. So what's the foundational basis behind this formulation? Well, it is dynamical triangulations, or the newer Lorentzian version that goes by the name of causal dynamical triangulations, or CDT. So what are the basic ingredients? They're really simple and they're really kind of time tested. So for one thing, we have the path integral, so the superposition principle, if you like, applied to gravity. So the path integral we are interested in quantum gravity is basically the sum or integral over all curved space-times, subject to some boundary conditions where the space-times here, so the curved space-times are indicated here by this little g, and this little g is an element of Lorentzian metrics where, of course, we have a gauge symmetry given by four-dimensional diffeomorphism. So a G is kind of an equivalence class, so a genuinely kind of a physical space-time geometry. And each of these, we're asked to kind of take a big quantum superposition of those, and each of them is weighed with a complex phase factor e to the is, where s is your favorite gravitational action. So that's kind of a declaration of intent of what one would like to compute. And in principle, if we have a well-defined prescription of what this object is and how to compute it, in principle, that gives us access to any physical information we would like to extract. Now, so what is CDT? Well, firstly, CDT builds on the previous formulation of the Euclidean path integral, so the one without the I here, that was in a regularized form, studied by using so-called dynamical triangulations. So what is the idea? Well, we don't really know, where little g, in what space little g lives. This is, of course, a functional integral, and you can take it to live in a regularized version of the path integral where you have approximated kind of smooth metric spaces by piecewise flat metric spaces. So the easiest way to understand how this works in this dynamical triangulations approach is to look at two dimensions. So what you do, let's, again, for simplicity, look at just the Euclidean version of it. So then the idea is you have a path integral or a partition function where you have to integrate over all two-dimensional, curved spaces. You represent them by simpler objects, namely by gluings subject to a certain topology, let's say of a sphere, of equilateral triangles, which are individually flat. And at a regularized level, you don't take infinitely many, but only n of them. And your task is then, in order to represent and compute this partition function, to glue them together in all distinct possible ways. And each of them will then be weighed with a phase factor z in the Euclidean cases in them e to the minus s, where s is just some version of the gravitational action, Einstein-Hilbert action. So this is kind of the baby toy example to test this kind of formalism. And it was actually first studied in the mid-1980s by physicists who were interested, theorists who were interested in a non-perturbative treatment of string theory. So they were interested in, at the time, what was bosonic string theory, in the non-perturbative dynamics of two-dimensional world sheets. And again, the idea was, well, let us simplify the description of the geometry of these world sheets by triangulating them. Yeah? So then you get to this type of formulation if you're choosing your strings to live in a zero-dimensional target space. Otherwise, you also can use these dynamical triangulations, but then you couple conformal matter fields to them. But that's the origin of the idea. Of course, it was then subsequently discovered that bosonic string theory doesn't really make sense. It contains a tachyon. And these models, however, kind of survived as interesting models of either what one calls non-critical string theory. And it should be said that in the meantime, mathematicians have become interested in them. Yeah. So for the pure gravity case, where this is just this two-dimensional path integral here, this now has become a huge huge industry where pure mathematicians study what we know as Liouville gravity, and or they call random two-dimensional random geometry. Or of course, it lies also in the same universality class as these dynamical triangulations. So if you're interested in all these developments, so it's a very, very active area. You should look at this preprint by Scott Sheffield. So that's an aside. So one point I'm making here is you're of course not interested in kind of these finite dimensional triangulations, but in the end, you're always interested in taking a continuum limit where kind of these building blocks shrink to zero, these individual building blocks, and you take their number to infinity, and you try and understand whether there is an interesting scaling or continuum limit behind these systems. So in 2 dimensions, this can be done. So you obtain, to get a flavor of what these geometries look like, look here at this beautiful kind of spiky two-dimensional random geometry with the topology of a sphere. Yeah. So you see that as individual geometries, this is very, very different from a classical smooth curved surface. Yeah. And this is really captures the nature of these random objects. So why are they called random geometries or random surfaces? Well, it's a higher dimensional version of random walks. And of course, we know many things about random walks, but if you think of random, walks as obtaining them from a limit of piecewise kind of straight walks, they're also very spiky and kind of nova differentiable objects. So what we are finding here in higher dimensional random geometry, we find also that typical such objects then that will contribute to the partition function of the path integral also look very, very non-classical. But in 2D, again, it's a beautiful mathematical structure. One can then look at these ensembles and define their continuum limit. And one can show that this continuum limit is a metric space, but of course with very unusual metric features. So this is a bit of history of the approach of random geometry. In physics, as happens so often, of course, there is a beautiful mathematics and new mathematics, but what we really need are variants that the mathematicians haven't yet explored. And in our case, number one, we need to change 2 things. We need to change things from Euclidean to Lorentzian. So we're describing space-times and not spaces. And we have to go to 4 dimensions because that's a dimension, of course, where real quantum gravity lives. And to cut a very long story short, the ambition to look at this generalization really led to the birth of what is nowadays called CDT. And this really goes back to a paper of Jan Ambjörn and myself, where we are looking at these Euclidean objects in 2 dimensions, and first of all ask ourselves, hey, is there perhaps a more physical Lorentzian version of it? And it was triggered by the fact that if you generalize this Euclidean construction to higher dimensions, unfortunately, people didn't find any interesting continuum limits where the geometry of the continuum limit was kind of extended and recognizable, at least in some limit as reproducing classical extended space-time. So there was seemingly something wrong with it. The conjecture was maybe it's the fact that it's Euclidean path integrals and not Lorentzian ones. And we explored this first in 2 dimensions. And just to give you an idea of what you do going from Euclidean to Lorentzian, well, in 2 dimensions, say, instead of using equilateral flat triangles, where all edges are the same, you actually work with Minkowskian building blocks. But the more important thing, in a way, is then how you glue these objects together, these Minkowskian building blocks, to obtain approximations of curved spacetimes that you then integrate over in the path integral, are kind of the gluing rules. So the gluing rules in CDT are defined such that there is an overall kind of a coherent light cone structure. So you see with each of these building blocks, of course, if I want to, I can draw where the light cone goes. And then the gluing rules are such, first of all, that you always glue time-like to time-like and space-like to space-like, but also such that there is a kind of an overall forward flow of time. Yes. So this is what then makes the essential difference. And if you do that, you look at the piecewise flat objects you get by applying these kind of causal gluing rules. They are very different from what you get when you do arbitrary gluings of these Euclidean objects. And this is why these 2 types of models can lead to very different continuum results. So in 2 dimensions, one can derive, analytically soluble models and shows that they're inequivalent. In higher dimensions, they're also inequivalent. And the beauty is that the Lorentzian version does seem to give very interesting and physically interesting results, where the Euclidean version didn't do that. So I want to step back now. I've talked about random geometry to ideas that people have followed for a long time. And that is, exploring quantum field theories beyond perturbation theory. Of course, we don't have so many techniques and general strategies of doing that, but what we do, for instance, when we look at gauge theories and want to understand, say, the non-perturbative aspects of QCD, we put that theory on the lattice. Now, the idea to put also gravity on the lattice has been around for a long time. So what is the general idea behind this strategy? So the lattice, as I've written here, acts as a regulator. So instead of smooth space-time, you set up your space-time as a hypercubic lattice, and you put the fields on it. The lattice edges have a certain length, A, which is your ultraviolet cutoff. And of course, in the end, you want to shrink this A to 0 so that the lattice then approximates ever better your continuum spacetime and your continuum field space. What you do then, as you take A to 0, it's not automatic that you find an interesting continuum kind of interacting field theory, but what you have to look for is for a second order phase transition, where in which in the neighborhood of which you can take a limit in which most of the unimportant kind of regularization details of your discretization drop out. So that's, of course, what's behind this is a whole logic behind statistical systems, and you'll be familiar with if you studied statistical mechanics, let's say, or statistical physics of an easy model. Yeah, so interesting continuum behavior you only find in when there is a divergent correlation length in the system, and that is typically associated with a second or higher order phase transition. And while taking the lattice spacing to 0, one typically also has to renormalize the back coupling constants of this lattice theory. And then if all goes well, one then attains what one calls universality. So exactly an independence of many of the ad hoc or arbitrary regularization details one used to set up the lattice theory in the first place. So if you wanted to use this for gravity, this logic, note it's different from just discrete, what people may call discrete gravity, where they postulate there is some smallest fundamental building block, and everything is constructed from these building blocks. Now, many people favor such approaches. The problem is that they're highly non-unique, and if you don't have a mechanism by which universality is attained, every little different discrete model will give rise to different quantum dynamics. So that's not what one is after here in what I call kind of lattice gravity. Now, so if this works, it's a beautiful and powerful technique, as you also know from QCD, but of course it's subject to numerical limitations. But again, if the continuum theory is there, it's essentially unique by these mechanisms. For a long time, people have tried to put gravity on the lattice or quantum gravity on the lattice. So very briefly, so I divide this in two types of approaches: a naive type of lattice quantum gravity approach, which people followed from the late 1970s onward. And it was very much inspired by lattice gauge field theories, which of course were very, very popular and already successful at that point. So in order to put gravity on the lattice, to imitate as much as possible what happens in gauge theory, one best uses a first order formulation of general relativity, where you don't work with a metric, but instead with kind of vierbinds or tetrads and connections, so spin connections. The important thing is to have a connection there, because a connection, is somewhat similar to gauge connection. You will associate it with the edges of your fixed hypercubic lattice. So people studied a variety of such models, and on fixed hypercubic lattices, really imitating lattice gauge field theory, but unfortunately they never saw anything interesting. So no hint even of second order phase transition, no hint that anything interesting was going on. So I would say it was a little bit mysterious, for why, but there is a very kind of a big elephant in the room for probably why none of these approaches worked or saw anything interesting, namely that the way in which you just put kind of by brute force the kind of the G mu news or the tetrads in this case and connections on a fixed lattice very badly breaks diffeomorphism symmetry. So you break it so badly that you don't even see that it's ever been there. And messing so strongly with one of the fundamental symmetries of the system probably made these types of approaches doomed. Now, by contrast, there was what I call a not so naive way of putting gravity on the lattice, which originated roughly at the same time, and which is based on this beautiful idea of Regis, Tullio Regis, famous Italian physicist, who in 1961 wrote a paper called General Relativity Without Coordinates. And what was his motivation? He was interested in solving Einstein equations away from situations with strong symmetry. This is typically, of course, our solutions, spherical symmetry, cosmological homogeneity, isotropy. Then we can solve the Einstein equations. But if we want to go beyond that, what can we do? Well, so his idea was indeed to triangulate, to approximate the curved spacetimes by triangulated objects. So to substitute smooth manifold M with some G mu nu by a triangulation T together with edge length assignments, as indicated here. So in his approach, these edges, they can all vary, and he gave a way to discretize in the same framework the gravitational action to what we now would call, the Reggie action. So to rewrite really the classical dynamics, so the action, but also the equations of motion, the Einstein equations, as functions of these length variables, the length of the edges of a triangulated approximation of spacetime. And where I would say the beauty is really the fact that you never have to invoke coordinates. You never have to introduce any coordinates. So you only have these edge lengths, and they're essentially, there is no, the diffeomorphism group doesn't act on these anymore. They're kind of true geometric degrees of freedom. So it's kind of a manifestly diffeomorphous and invariant way to think about geometry and even dynamical geometry classically. So in a way, what one is doing in DT and CDT and also quantum logic calculus, one is making use of this fundamental insight. And it has a beautiful technical consequence, namely that you do not anymore have to worry about gauge fixing issues in the path integral, for the diffeomorphisms, because you're already working with geometric degrees of freedom. So it's an enormous simplification. If you have ever worked yourself with a gravitational path integral, it's of course very tricky to do gauge fixing properly. So this is what this approach takes care of. It has been applied classically as this Reggie calculus, as it's called, but it hasn't been shown to have any very specific advantages there. However, I would claim when it comes to the quantum theory, and especially in terms of these implementations where you're using equilateral triangles or triangles that are simple, like Minkowskian versions of equilateral triangles, the whole power of this idea really unfolds. So I should also say, well, there is a remnant of diffeomorphism invariant, which you will find when you try and work with these triangulated objects, because you have to, for instance, if you in higher dimensions you simulate these objects, of course you have to give name to the objects, to the triangles or the other subsimplices of your triangulation. But it's very straightforward to arrange things in such a way that everything in the end is labeling invariant. So we have generally taken care of the gauge, the big and nasty gauge invariance of gravity in this way. Okay, so here comes the key object we are working with, right, is the path integral, or what becomes of this in this specific approach using Lorentzian random geometry. So here on the left, you see the formal path integral, right? So this is very formal in the sense that, well, we need to specify precisely what space we are integrating over here, what the measure is, and how we do the computation before this becomes a real, a well-defined object in a mathematical sense. So here, for definiteness, I'm working with the Einstein-Hilbert action, so with the curvature scalar and the cosmological constant term. So this is the formal here on the left-hand side, the formal continuum object. CDT is a precise prescription how every one of the ingredients of this path integral is to be interpreted and formulated. So this is kind of the well-defined version of the path integral, at least as long as you have a finite number, capital N, of building blocks. So what you're doing is you are with a a specific kind of weight factor, which depends on C of t for a given triangulation. That's the size of the automorphism group of the triangulation. So the number of ways in which you can map the triangulation in non-trivial ways to itself. And other than this, it's a kind of a completely democratic sum over all causal triangulations you can build from your elementary building blocks with causal gluing rules, and each one of them is weighed by a phase factor which uses the Regis version of the Einstein-Hilbert action in this discretized or piecewise flat formulation. And then the non-trivial thing is then to say, then we take a continuum limit of this object with the same logic as I explained before, of lattice field theory. So again, it implies you're not interested in the finite triangulations, but again, this continuum limit is very essential. So how do you think of that now in higher dimensions? Well, you have, still little a, your UV cutoff, essentially the linear size of your building blocks. You have the number of building blocks. So what you do is typically you send the number n to infinity, keeping kind of a physical 4-volume fixed. Yeah. So that also, of course, implies that a is sent to 0. Now, here again is a side remark about the gluing rules. So the space-times that in the CDT path integral you're summing over here, they obey kind of a discrete version of global hyperbolicity, which is, of course, the causality constraint you impose in the classical theory on all solutions to the Einstein equations. In the quantum theory and in the path integral, there is absolutely no rule that tells you that the individual kind of the path or the individual kind of virtual space-time histories should obey such a condition. Yeah. So because we know in general, there's very, very non-classical geometries can contribute to the quantum path integral. But the statement here is, if you impose this condition on your individual histories, then you arrive at a specific path integral, and we derive kind of beautiful physical results. So it's an outcome of an experiment, you could say, whereas in the old DT Euclidean approach, one never saw anything interesting in higher dimensions. This seems to be completely changed once we impose this kind of the causal structure on the individual path integral histories. So one way of phrasing is so one thing we seem to have learned is that, of course, people who've advocated the Euclidean path integral for gravity in the past, well, they would say, okay, look, let us, take a sum over spaces instead of a sum over space-times. Let's solve it, and in the end, let's look at the result, and it will tell us probably how we should rotate it back to Lorentzian signature. So the problem with that approach, however, was that one never did see anything very interesting coming out of the purely Euclidean path integral. So here, now it seems that time doesn't emerge, and causal structure also doesn't emerge. So the lesson for the time being is apparently these are things you have to kind of put in by hand into the path integral. Otherwise, they will never re-emerge in whatever, quantum space-time or so you hope to get out of this. And of course, in principle, general relativity should re-emerge or come out as a classical limit from such a quantum construction. Now, obviously, we are in 4 dimensions, and although we can solve these random geometric models analytically in 2 dimensions, and some brave souls and even mathematicians are, taking first steps in trying to understand maybe what happens in 3 dimensions. In 4 dimensions, analytical methods are currently not sufficient to understand what's happening with these path integrals, not even in an asymptotic sense, which of course is all you need here. So one has to rely critically numerical methods, and in our case, these are Markov chain Monte Carlo methods. Yeah. So this is what we are using, and we're using it really in the spirit of, lattice QCD to obtain information about the limit of the path integral. So here's a precise prescription of what we are doing, kind of theoretically speaking, and extract interesting information via observables, etc. Okay, so here's a 4-dimensional Minkowskian building block. So that's these building blocks we are gluing together, in 4 dimensions in order to make sense of this path integral S, and then taking the limit here. So that's Lorentzian random geometry. So that's really the underlying toolbox. Having this toolbox, so what are you going to do with it? What are we computing? So let me tell you what we have done, but in general, not. I mean, I'm talking about what people have done in this approach, and what form. I mean, what the quantities are that one can study quantitatively. So what one does really is one tries to understand. Well, has of course the path integral, but then one tries to understand its properties, or the properties, let's say, of its ground state, of the vacuum state of that theory. And this one does by evaluating appropriate operators, which I here call O, in the sense of expectation value. So by inserting them into the path integral in the standard way. Yeah. So here now I should say, you could say, oops, where has the factor of I gone? So what CDT has, which is very special and is not present in the continuum, it has a well-defined analytical continuation, which really, when applied to the path integral, rotates the e to the is path sum to a Euclidean analog. So there is a precise prescription of Wick rotating every single piecewise flat Lorentzian geometry to a given Euclidean geometry. Now, why do we need to do that? We need to do it because we need to have a real partition function in order to be able to apply our Monte Carlo methods. They really need real Boltzmann weights, and they cannot deal with complex weights. But the logic is, of course, the same as in standard quantum field theory. It's just a mathematical trick. It's an analytic continuation. You do analytically continue to Euclidean signature, and it's not an ad hoc thing, but it's a precise mathematical prescription. You then solve that path integral, and of course, in the end, you still have the task of reinterpreting your results or Wick rotating them back to Lorentzian signature. So this is exactly what one is doing here. Now, what is special here about the observables one can study is they, of course, they have to obey the symmetries of the theory. So that is still a non-trivial thing to implement. So, and it's different, and it goes beyond what happens in Young-Mills theory. Yeah? So, of course, if we do Young-Mills theory, I mean, perturbatively or non-perturbatively, we are also interested in gauge invariant observables, right? Because they contain the interesting physics. We're not interested in the gauge degrees of freedom. And if you were in, Young-Mills theory or even electromagnetism, you would work with local invariant quantities. For example, you have, of course, say an F mu nu, but the F mu nu is not an observable because you still have free indices. So then you just say, okay, let me compute F mu nu with indices constructed. That is a local gauge scalar, and that's one of my observables. That is not enough in a diffeomorphism invariant theory like gravity or quantum gravity. So here we are looking at pure gravity, because even if you have a scalar here, let's say like the Ricci scalar, of course, if you like the x, the argument x, it depends on, this is simply, it refers to a point x or a label x that is just not a diffeomorphism invariant object. I mean, you don't know, if I give you an ensemble of geometries and I tell you compute the expectation value of R of X, you just have no idea where the point X is in all of these different geometries. So that's another way of saying, well, R of X itself is not a good observable. But what is a good observable is, for example, the space-time integral of a scalar like this. So in the simplest case, just the space-time integral over the entire manifold of the Ricci scalar. Yeah. Of course, it's non-local, but this is in the nature of gravity, so it's not approach specific. So typical diffeomorphism invariant observables we can study in pure gravity, pure quantum gravity, have this non-local character. It still doesn't mean that they're not interesting or we cannot say many things, but it's different things we are able to access and also different types of physical statements we're able to make. And having come to this point, it also, one needs to handle expectations of what people are asking from quantum gravity. Because in this genuinely, in a diffeomorphism invariant background independent formulation of quantum gravity, this is what will happen. These are your observables. But often what people's favorite questions to quantum gravity are, they come from a semi-classical context. Yeah? And unfortunately, it's the nature of the game that these, unless you reformulate them in terms of genuinely diffeomorphism invariant quantities and background independent quantities, they are not directly accessible in such a non-perturbative regime. So, for example, if your favorite question has to do with, let's say entropy associated with a black hole horizon, well, unfortunately, that already tends to refer to a very classical or semi-classical situation where you already have such a background geometry there. And it's very difficult to rephrase this in a non-perturbative language. So many of your favorite semi-classical or classical flavored question about quantum gravity do not have an immediate Planckian implementation. And that's not a fault of any formalism. It's just a feature of what quantum gravity is about and what we can also expect it kind of to do for us, to yield in terms of results. So is there anything interesting we can learn from such an exercise? Well, there is already one prediction, a number or a quantity that is so exciting because there was never anything to compute in quantum gravity. I mean, beyond, perturbative or effective observables that are of the type of, corrections to classical results, in some effective way of thinking about quantum gravity. So here's a true quantum signature. So what it is about a notion of dimension you can introduce in this fully non-perturbative context for these very fluctuating quantum spacetimes or quantum geometries that you're dealing with. And that is a notion of a spectral dimension. And the spectral dimension is the dimension seen by a random walker, or equivalently by a diffusion process. So what is the beauty of this idea? The beauty is that, someone hands you an unknown space. It may not be very classical at all. You set up a diffusion process. So it's like, I give you a bucket of water, you let an ink drop fall in, and then you monitor how this ink drop spreads as a function of time, diffusion time. And from the growth of that ink cloud, you can deduce what the dimension of the space was that you are looking at, that you are, exploring with this diffusion process. So that is the spectral dimension. And the beauty is that this can be set up in very, very general spaces. Basically, whenever you have, some kind of Laplace operator floating around, you will have diffusion and you will be able to extract the spectral dimension. And the same is true in quantum gravity. And the same is true for these kind of random geometric formulations of quantum gravity. And back in 2005, we made this experiment with, in 4-dimensional quantum gravity, my collaborators Ambjörn and Jukiewicz and myself. And we found, to our surprise, that the spectral dimension in our quantum geometries was not 4. It was only 4 on large scales, but when we looked at short diffusion times that explore just, locally the quantum geometry, the spectral dimension was more in the vicinity of 2. So that's what we measured in the simulations, kind of with error bars, of course. And so the beauty is there is a number that could be extracted, as in our case with error bars. And after that, over the years, many people went to their own approaches and try to compute also a spectral dimension. And many of them reproduced this, what we call a dimensional reduction. So from 4 macroscopically, kind of on classical scales, to something like 2 or in the vicinity of 2 near the Planck scale. And in the best of all worlds, of course, this would be, we may have discovered a universal property of quantum gravity. So that doesn't even depend on the approach. And especially Steve Carlip has written papers about it and speculated about the possible universality of this. So whatever the outcome of this analysis, I would say the beauty for me is, number one, there is something we can compute. Even if at this stage we don't know how to relate it to phenomenology, what is the effect, I don't know, on gravitational wave propagation of the fact that, at tiny distances, space-time may look 2 instead of 4-dimensional. We don't really know this. But the beauty is there is a well-defined, operationally well-defined operator whose spectrum we can understand, so numbers coming out, and we can do that in various approaches, and that will enable us to compare these approaches and also say, okay, we are getting the same number. Is there a deeper reason for why we get the same number? Or if we don't, is this approach better than this other approach? So this is to illustrate there is something rather than nothing, even if you're working with these, averaged and non-local observables that describes this Planckian regime. But of course, understanding what dimension of quantum spacetime is certainly not enough information. I mean, in 2 dimensions, it gives you a lot of information looking at the spectral dimension, also the Hausdorff dimension, but we expect more. We want to understand more in the case of 4 dimensions. We want to understand more about, kind of local geometry. Can we say anything? And the answer is yes, over time, we have discovered various ways to understand the physical geometry. So the first thing we discovered beyond the dimensions is kind of and that is relatively easily accessible, is what I'd call the shape of quantum spacetime. So what I mean by this is the 3-dimensional volume as a function of time, measured in the ensemble and of course evaluated in the sense of expectation values. So T is a kind of a proper time, kind of cosmological proper time that one has easy access to. And what we measured and monitored was, so what is this shape? And what you see here in this little graph, that's the outcome of the measurements in 4-dimensional, of the 4-dimensional path integral in one of the phases of this underlying statistical mechanical model of 4-dimensional random geometry. So fascinating. So you saw these blob pictures on one of my previous slides. So here is kind of all the blobs put together to get a mean value or expectation value of the shape. And what you see here is the data. There is a curve, an interior curve, and there is also a theoretical curve, a cosine cubed curve that virtually falls on top of the measurement curve. And what is the significance of the cube, of the cosine cubed? It's the shape of a Euclidean de Sitter space. Of course, we have rotated. Yeah. So if you like, what we are comparing to are Euclidean space, and just for the scale factor or the three-dimensional volume of this universe, we can compare it with a line element of a cosmology. And this cosmology is, of course, that of de Sitter space. And you see here, this just is in a kind of proper time coordinate system. That would be the corresponding de Sitter space S4 round sphere metric that shares the same volume profile. Yeah? So this is beautiful. So the mean value, the expectation value of the shape of our dynamically generated quantum universes fits a classical expectation. But there is more than this, because we can also analyze low-lying eigenstates of the fluctuations around this mean value. And we can also have been able to map them on a semi-classical expectation that you can just do. You can just do an analytical calculation around de Sitter space. And you also find a beautiful match here. So that's a bit of an old story, but I think nevertheless important highlighting, because we've superposed really crazy looking geometries and without putting in any background, and what comes out is at least one observable, one variable that characterizes this geometry that we can map onto a classical quantity, a well-known quantity. So what one should be careful about is now to say, aha, so you have shown that you've rederived de Sitter space, from your non-perturbative path integral, but that is not correct. We have only made a statement about one of the modes of the metric, the volume mode or the global Friedmann mode or Friedmann factor, whatever you want to call it. Yeah? And its behavior, indeed, we can match onto a classical expectation. But we already know that locally, these spaces are extremely quantum fluctuating. And the question is there any other way in which we can pin these quantum geometries down, again in the sense of expectation value, that makes a more specific statement about what the local geometry looks like? Of course, the first thing that comes to mind, talking about de Sitter space, right, looking at this line element, well, de Sitter space is, of course, a highly, highly symmetric space. It's isotropic and homogeneous. It's a constant curvature space. So can we look at our quantum space-time and say anything about its local curvature? And that's, of course, where the trouble starts, because, this is what the geometries look like. They're totally spiky. There is no tensor calculus. They're kind of nova differentiable. And how can you even dream of evaluating anything like, say, the Riemann tensor, which depends on, of course, derivatives of the metric. Now, the new story, which I'm able to only very briefly summarize for you in the following slide, is we have now found a notion of curvature that does make sense on these crazy non-differentiable spaces, and we can use it as a kind of, and is finite in the continuum limit. So it really gives you a kind of normalized notion of curvature. And more than that, it's Ricci curvature. And we have used this notion to actually explore the outcomes of these quantum geometries. So very briefly, so what is this quantum Ricci curvature? Well, it's a notion of curvature beyond Riemann. So it is inspired by results in pure mathematics, where people do study especially notions of Ricci curvature that apply in more general spaces than smooth Riemannian or pseudo-Riemannian spaces. So and here the reference I'm citing here is by a mathematician, a French mathematician, Olivier. So he constructed what is now called the Olivier-Ricci curvature. And what I'm presenting to you for application in quantum gravity is kind of a variant that is useful in the context of quantum gravity. So what is the main idea? the main idea is explained easily for a smooth curved space. So imagine I give you just a Riemannian manifold of any dimension. So in order to understand what its curvature is, I don't give you the G mu nu, and I don't give you, the Riemann tensor. You don't know what that is, but you are asked to set up a geometric experiment to understand what the Ricci curvature is. And the thing you do is the following. You pick 2 points, P and P prime, that are a distance delta apart. Okay? You draw 2 geodesic spheres around these 2 points of radius epsilon. And what you then do, you compute the distance of the sphere around P from the sphere around P prime. It's not so critical which notion of distance you adopt. Yeah, it's of course a notion of distance between 2 extended objects. The notion of distance we apply for our applications is we are averaging over the distance of all pairs of points that come from these 2 spheres. So as is captured here by this formula at the bottom. So this is the distance of sphere 1 and sphere 2, right? We are taking all q's and q primes from these 2 from these 2 spheres, look at their geodesic distance, and integrate them over all q's and q primes, and then divide out by the volumes of the 2 spheres to normalize it. So we have an average sphere distance. Now, the sphere distance criterion underlying this construction of this understanding of the generalized Ricci curvature is the following. When you sit on a space with positive Ricci curvature, the distance of these 2 spheres will be smaller than the distance of the centers. And conversely, when you sit on a space with negative Ricci curvature, the opposite will happen. Namely, the distance between the 2 spheres will be bigger than the distance of their centers. And to extract, so this is a criterion you can use on a Riemannian manifold, and there, in the limit then, as you take these spheres small, and let everything kind of shrink to a point, you rederive standard classical Ricci curvature. But the beauty is you can apply this on general metric spaces. The only thing you need to be able to do is measure volumes and measure distances, geodesic distances, and that you can do. You don't need smoothness. So what do you then actually do in order to extract the Ricci curvature? You take the quotient of the sphere distance with the center distance. And what will happen basically is you get a constant term that depends on various things, plus a correction term that is not constant as a function of delta. It's not non-constant as a function of delta. Yeah? And this this is what you call the Ricci curvature, the quantum Ricci curvature at coarse grading scale delta. And where on the previous slide I drew, I took separate values for the radius of the spheres and the distance between their centers. In order to have only one length scale floating around in quantum gravity, we choose them to be equal. So what we're doing is we are computing sphere distances of 2 spheres of radius delta whose centers are also a distance delta apart. So we have the delta, of course, straight away, and then we compute, we measure, we use computing geodesics, we measure, we construct the delta spheres, and then we compute distance between those 2 spheres for given delta, and then we extract this Ricci curvature. So the beauty is its very general applicability, the fact that in a classical setting, it reduces to the standard notion of Ricci curvature. And the beauty, of course, is that we can apply this in quantum gravity to extract curvature. Now, how does this thing behave, this KQ, as a function of delta? Well, in order to understand it, we measured it on simple classical spaces. Because, of course, you cannot read it off immediately, even if you just know, say, the Riemann curvature tensor, but it's a slightly, quasi-local, slightly non-local a construction we are making. So, however, on constant curvature spaces, you can actually compute it analytically. And just for illustration, I've just plotted 3 cases for you here. They look very similar in any dimension, and they characterize what we call the volume profile, namely this quotient here as a function of delta for a constant positively curved space, a constant negatively curved space, and a flat space. And you see, as a function of this delta, this coarse graining, totally different behaviors. For a flat space, there is no correction term. So this is there is a flat line. For hyperbolic space, KQ is negative, and therefore this curve, ends up being above this flat curve. And say on a positively curved space, this thing is the curve runs here in this characteristic shape below the constant case. So you're subtracting a positive number there. Now, so what we do, so these are our reference, kind of fingerprints for the curvature profiles of very nice classical spaces. When we evaluate the same curvature on these crazy, quantum spaces, we use this as a reference to, in the first instance, understand, is this space flat? Is it negatively curved? Is it positively curved? So, so let me show you what we've done to convince you that it's a really interesting and important new tool. So this is a typical two-dimensional space-time coming from the Lorentzian path integral in 2 dimensions. Yeah? So this kind of candlestick, very, very quantum fluctuating. Time is going upwards. So are we able to associate a curvature with it? The answer is yes, using the Ricci curvature. And here you see the outcomes plotted. So this is for increasing volumes. So you see where the curves go down. These are actually kind of finite size effect. So what you should concentrate on is the measurement points for the largest of the volumes we've chosen in the simulation. This is orange line. So what we see is some initial discretization artifacts, which you should ignore. And then we see a kind of curve that is not flat. So you might have thought, okay, these are kind of tori, discretizations of tori, and that's true. But the curvature that they have is definitely not approximated by that of a kind of flat torus, but it's what we call quantum flat. So here is the result. Even more curious, I would say, is now asking what is the curvature of a typical space-time that contributes to the path integral of 2-dimensional Euclidean quantum gravity. So that's Liouville gravity. So it's one of these spiky things. So what one of my PhD students and what we've been able to do is exactly look at the expectation value of this quotient and match it magically to the volume, the curvature profile of a continuum sphere. However, the surprise was that the best match is to a 5-dimensional continuum sphere. So this is 2-dimensional Euclidean quantum gravity. Of course, is a very, very fractal geometry underlying this. So, but that's the finding. So, interesting things happen. Now, what motivated this whole story was, of course, can we say something about the curvature, the quantum curvature of this de Sitter universe, or this candidate de Sitter universe, where we've identified it has the shape of a de Sitter space, but otherwise we don't know. It may not resemble a de Sitter space with respect to other properties. But what we were able to do is to study the curvature profile in the same sense I explained on the previous slide. So we did that in CDT for the non-perturbative path integral. As usual, implemented with on topology, space on topologies S3 cross S1, with volumes of more than 1 million building blocks. And then we implemented this quantum Ricci curvature, or rather the scalar. So we're just extracting the scalar part of it. So what we definitely see is that this quantum scalar curvature is positive because the curve goes down. And we can also give a reasonable match to the corresponding curvature profile of a 4-dimensional continuum sphere. So here we have some additional support that indeed also, with respect to this very integrated average mean value of the curvature of the Ricci scalar, our de Sitter space does indeed also here resemble the continuum space. Now, this before wrapping up, what I'm very excited about is that we now have this notion of quasi-local curvature, and that enables us to access a whole raft of interesting observables which we weren't able to before, because we only had dimensions. We didn't have any local geometric characterization of these quantum geometries. So what we have already used them for is to construct measures of homogeneity. So that's the next step, looking at our de Sitter universe. It has a certain average curvature, but we have said nothing about, again, the quantum wiggles. It's still very highly quantum fluctuating. So what one wants to have, if this is supposed to be, let's say, representing, de Sitter space in the very early quantum universe, one wants to understand, well, how homogeneous is this space? How isotropic is this space? And you don't understand this just by looking at it. I mean, you have to ask the computer the right question. You have to ask the right questions to this, if you like, this vacuum state that comes out of the non-perturbative path integral. And we've been able to define a kind of quantitative measures of homogeneity. So I don't have time to explain it now, but this gives us a handle indeed on the degree of homogeneity of something like the curvature. We have only so far applied it in 2 dimensions, but it will be applied in 4 dimensions. And we will be able to extract even more information about this dynamically generated de Sitter space. Now, a very, very important thing to understand, of course, quantum field theory in general, but quantum gravity in particular, is to look at correlation functions. And also here we were lacking an interesting local, well-defined quantity or quasi-local quantity. But now we have this quantum Ricci curvature, and we can look at 2-point curvature correlators. And again, we've run a beautiful pilot study in 2 dimensions on 2-dimensional Euclidean path integrals. So this is also with a student of mine. And this is something we will also generalize to 4 dimensions and extract real physical, hopefully interesting information. So that brings me, I'm stretching my time, but this brings me to summary and outlook. So, of course, I've gone through and given you some glimpses, of what this approach is to non-perturbative quantum gravity. And here on this last slide, I'm summarizing and also giving you, kind of, so what does this represent as an approach? What is the type of quantum gravity, image of quantum gravity that comes, that this represents? So I would call it, number one, I would call it, because of the importance of, extracting quantitative information in order to construct the theory as such, I call it an approach of computer-assisted quantum gravity theory construction. So we're getting genuinely new insights from putting the theory on the lattice. And of course, it's kind of a strongly coupled system, and there are not very many handles we have beyond perturbation theory. So it makes, of course, quantum gravity look much more, in terms of methodology, as the way we're studying it, as a complex system, and a strong, as I said, a strongly coupled system. With, of course, it leads to certain expectation also of the type of information we will be able to extract from this. It's not so much writing down and solving exact equations, but it's looking for universal properties. It's, scaling behavior of selected observables. So that's a way to study this. As I already highlighted, it requires some expectation management of what a theory of quantum gravity of that type can deliver. So it's observables, but the observables have unusual features. They're non-local. but nevertheless, as the example of the spectral dimension shows you, they can contain new quantum signatures, and of course can contain, in principle, can lead to phenomenological predictions down the line. I would say probably most, I'd say something more about this in a sec. So the underlying mathematics I've highlighted in passing is beyond Riemannian, and it's a framework of random geometry, but also another branch of mathematics where this notion of Ricci curvature came from, is kind of discrete mathematics, or studying curvature in non-smooth general metric spaces, and that's something mathematicians are interested in. So it's very interesting that they have come to this within their intrinsic mathematical motivations, and we in quantum gravity also coming, of course, with physical motivations, and there is some convergence of ideas. And as I said, in 2 dimensions, this random geometry in mathematics is an absolutely booming subject. Now, CDT, what I've talked about here, you should really think of as a toolbox. So it's kind of minimal, non-perturbative quantum extension of general relativity, where it seems we can reliably do computations in the vicinity of the Planck scale. And it has already produced interesting results. So emergence of this de Sitter-like space from first principles, where we have already shown some of its properties having well-defined classical limits. But of course, we're interested also in the quantum aspects, so quantum signatures. The clearest path from this to any phenomenology will be in early universe. That's what I believe. So, for instance, we are studying what I briefly mentioned, 2-point functions. Why is this important in cosmology? Well, 2-point functions, if you look at seeds for structure formation in early universe cosmology, before the onset of inflation, people, of course, work with kind of ad hoc de Sitter-like backgrounds on which they superpose, some quantum fluctuations of some infraton field. Now, what we may be able to do is to suggest, coming from the full quantum gravity theory, a scenario which may resemble this, but may also, have important differences. And there may be purely quantum gravitational ways of seeding structure. There may be interesting ways in which the universe shouldn't maybe be described by this idealized de Sitter space, but it has structure, and maybe our quantum gravity theory will tell what it is. So thank you so much for your extended patience, and I'm happy to answer whatever questions you may have on the talk.
Okay, Renata, thank you very much for your very interesting talk. Questions, please. I see one question from, no, there are more than one. Okay, I don't know who is this person. Betal, please ask your question. Who is this?
Yes, am I audible?
Yes. Stefania.
Excuse me.
Yes, please ask your question. 3453. No, yes.
What will be the effect of an interacting field with gravity on the quantum geometry?
Yes.
If you have an interacting field.
Yes. Yeah. So what I talked about, of course, was pure gravity. So statement number 1 is it is entirely straightforward to couple matter to it. So what you do is, for each of the geometries in the path integral, you add another, just a full, set of matter configurations. So these systems have been in 2 dimensions. They have been studied very much in the context of Liouville gravity, or also the Lorentzian 2-dimensional path integral. You can couple anything, conformal field theories, spin systems, Gaussian fields, what have you. And you can then look in principle, at a coupled system. Now, in 4 dimensions, we have also studied some matter coupling. There are 2 things to say. So again, you can couple, say, a scalar field in 4 dimensions. What we have not observed is that it has any strong effect on geometric properties. And you also can couple, say, we've thrown in a point mass, a dynamical point mass, and simulated this system. Also, that doesn't have a strong, it doesn't seem to affect the metric, I mean, the geometry in a strong way. So there's two, so one thing this may suggest is that matter doesn't matter at a Planckian scale. It could be that the geometric degrees of freedom are simply very dominant, but of course, more research needs to be done to do that. Number two, what is the challenge is to come up with interesting diffeomorphism invariant variables, including matter. Yeah. So, but that's more of a conceptual issue. But because it's not a regime, we usually think about, so the one really conceptual question is, so what is the question you ask of such a system? So what observable would you actually look at? That's interesting, that says something about this interaction.
Okay.
Is that sufficient answer for now, for your question?
Yes, ma'am. Yes, ma'am. And is there any requirement of an inflationary field? I mean, for the
well, of course, it's de Sitter, right? Of course, de Sitter, when you recrotate it back, is of course exponentially expanding. But I would not make any statement here, that we can describe the inflationary phase. I mean, it's really, I think what one extracts here is, of course, really the deep quantum era, yeah, and how far. I mean, so I should say something I didn't say during my talk. So we have a dynamical way of understanding in physical units how big the quantum universes are that come out of these simulations. And they are of the order of 20 Planck lengths across. So we are really sitting in a deep quantum regime, therefore. Yeah, just to give you an idea.
Yes, ma'am. And one last question: is there any kind of quantum geometry interpretation of gravity waves in this scenario?
No, for that, of course, you would already have to established, a classical quasi-flat background.
Mm-hmm.
But this is simply not present, and you wouldn't expect it at those length scales.
Yes, ma'am.
So asking things about graviton scattering are, I would say, physically and operationally meaningless at this length scale.
But can the gravitons come out as an effective field theory with this kind of close graining present?
Well, as I said, we cannot access this regime. We cannot access a semi-classical regime in this type of simulations. No, we can really. I mean, the strength of this is that we really look, in the deep quantum regime that is not reached by effective field theory.
Yes, ma'am. Okay, thank you, ma'am.
Okay, maybe we will go to the next question. The next question is from Oleg Tsirev. Oleg, please ask your question.
Well, thank you for interesting talk, and I have a couple of questions corresponding to comparison with latest QCD,
yes,
which you refer to. And first, corresponds to gauge invariance. Indeed, in QCD, all the observables are gauge invariant. From the other side, in gravity, the gauge fixing corresponds to the choice of reference frame. Does it mean that any such observable cannot be calculated in this approach? And second question corresponds to continuum limit. Usually, in QCD, the limit A to 0 should be accompanied with higher powers of A and with operators with derivatives, and they can be neglected due to query contributions can be neglected due to asymptotic freedom. Does it mean this is just my naive thought that this quantum flatness can be some analog of the asymptotic freedom in QCD?
Okay, so let's remind me of your first question.
Yeah, concerning gauge
invariant.
non-invariant quantities corresponding to some reference to choice of reference frame.
Okay, so I would say the best analogy of what we're doing in this this purely geometric language. So as I mentioned in passing, it's manifestly diffeomorphism invariant.
I
So
see.
and that is the analog, if you like, of thinking in terms of, I mean, Wilson's prescription.
Sure. But
and
usually we have the closed Wilson line is of course gauge invariant, but choice of reference frame, I think also this is important maybe for waves or for something is gauge, probably is analogous to gauge fixing. So probably in this approach, these observables are not accessible, right?
Yeah, well, look, there are no coordinates here.
Sure.
That's why I'm saying. So, but of course, you know what I said. Nevertheless, you know, I remember my explanation to say, well, R of X is not an observable. If you were treating it as an observable, but then when you then take its expectation value, since you don't know where X is, the point X in this, you would just again get 0 or infinity. So it's the same, I would say, as trying to, compute the expectation value of a gauge covariant quantity in gauge theory, and then you also get 0 typically. So the same thing happens here. As for so your second question is of course interesting. So what is the nature of the continuum limit here? Number one, and can I apply some standard QFT logic in describing the UV regime? The answer to the second question is we don't know. But so the most standard notion that people say we might be able to recover here is that the asymptotic safety scenario. So the existence, I mean the hypothetical existence of a fixed point of the renormalization group flow at high energies, which then renders all observables finite. So of course there has been you may be aware there is a huge industry using functional renormalization group methods to find, that has also found fixed points for the case of gravity. The fixed points are of course always found in truncated versions in the continuum, because otherwise you cannot do the flow computations. But in these truncated versions, people do see evidence of fixed points. Now, in principle, on the lattice, we should be able to find independent evidence for or against this scenario. Now, what we have here, we have second order phase transitions. We have made some prototypes of renormalization group flow studies in this phase space. It's very tricky computationally in the vicinity of these transition lines, and it's also tricky conceptually, because the question is, what is scale? What sets the scale, right? I mean, you don't have this problem when you look at the continuum limit of QCD on the lattice. The scale A is just literally the scale, but here scale is dynamically generated. So it's somewhat unclear to what extent some momentum scale people are using in these continuum considerations has a meaningful physical interpretation, and therefore whether this whole analysis is really meaningful at the Planck scale. So there are many unanswered questions. We have a couple of papers where we discuss renormalization in dynamical geometry. It's very tricky, but very interesting. And it's not, bottom line, it's not well understood.
Thank you very much.
Okay. The next question is from Richard Kerner. Richard, please ask your question.
Thank you. I was wondering, you don't impose anything on vertices when you consider a triangulation. The vertices can be from 3 to something, but what is the average?
Do you
impose Euler's theorem? The average. If average.
Oh, are you talking about two dimensions?
Yeah.
Yeah, in 2 dimensions,
Yeah.
No. I mean, of course, the coordination. So the rules are, of course, well, anything is allowed. I mean, you know, so it's a dynamical thing. So in this path integral, you know, like I give you n building blocks, and you glue them together in any, as long as you get a simplicial manifold, anything is allowed, and everything will appear in the path integral.
I'm not
and
sure
any coordination numbers.
because if the average is lower than something, it will be the curved space after all.
No. Okay. So two dimensions is special because the coordination number, because of Gauss-Bonnet theorem in 2 dimensions. So so the average coordination number is of course determined by the topology.
But in 4 dimensions, you have a second invariant.
Yeah, no, but it doesn't impose any conditions on the simplicial gluings.
And it wouldn't be something like Fourier transform if you consider the dual lattice, you know, like Voronoi lattice. No.
No. In higher dimensions, there are no topological restrictions. And I would say even in 2 dimensions, it's of course just one global condition. You know, it's a very mild thing. It doesn't restrict your local dynamics in a big way.
Thank you.
Yeah.
Okay. The next question is from Hong Wu. Please, Wu, ask your question.
First of all, thank you for your very nice talk. Yeah, I have a question. What happens if we work CDT on the ADS spacetime and what the CDT maybe use the solution of information paradox of black hole.
Yeah, your line is very bad, but I try, and I hope I understood your question correctly. So you asked about the relation to ADS space?
Yeah, ADS.
So
ADS space.
Do you mean, of course, ADS space is of course a single space, but here, of course, we are doing a path integral over all possible geometries. Right. I mean, of course, you could be talking about what boundary conditions do I impose, and of course, in simulations here, of course, I cannot. Well, of course, all my spacetimes are compact and finite, so I cannot. I cannot study asymptotics, if you like, be they flat or be they de Sitter or anti-de Sitter. So I'm confined in terms of my boundary conditions onto some compact spaces.
Okay.
But of course, I'm not fixing the geometry. Of course, in principle, I could find that on average, this object wants to have a negative curvature as a dynamical effect. But that's not what I found. So I found indeed that it has a positive average curvature. So
yeah. So
so your second question was remind me.
The second question, what immersion? What is emergence of symmetry in universe.
What is the emergent symmetry of the universe?
Yeah, in the CDT theory.
Okay, so
Yeah.
So this is in part exactly what I'm trying to understand, right? So we have this, kind of vacuum state that we're finding in the simulations, and of course we're trying to establish its properties. And I briefly mentioned, on one of my last slides, that we have now ways to, at least in a statistical sense, to measure homogeneity, for example, right? Which is, of course, something you're interested in for cosmological comparisons, or applications. So we have now a statistical measure of homogeneity, and we are in the process also of having a measure of isotropy. So once this has been constructed and applied in 4 dimensions, we will be able to give a quantitative assessment. I mean, how homogeneous does this space look on a certain length scale? But it's not, I should emphasize, it's not automatic that these quantum fluctuations kind of, cancel out or something. These geometries are very, very non-classical. So a priori, it's not clear, that somehow, it will boil down to something that I can interpret as a nice classical geometry with kind of small quantum wiggles when I zoom out. So that's something one has to really measure quantitatively. And it's one of the next projects we are currently working on.
Okay.
Okay.
Yeah.
Okay, let's go to the next question. The next question is from Ilya Shapira. Ilya, please ask your question. Are you here?
Hello, yeah. At some point, you mentioned that the observables in diffeomorphism invariant observables are related to the integral, which is actually the Einstein-Hilbert action. What do you mean by that? Why this action is an observable?
No. The action is not an observable. The Einstein-Hilbert action just appears in the path integral. So if I compute the expectation value, I just insert, of course, this operator into the path integral. I mean, this is just a standard way. Maybe you misunderstood what I did. It's just a standard way in which, I evaluate the expectation value of an observable in a quantum field theory in a path integral. So
okay.
Probably
so it was written on the transparency. And the second question, you speak sometimes about renormalization. What do you mean by renormalization in this approach? Because it's not perturbative, no divergences. So what do you mean?
Yeah. So, but well, I have, of course, I have discretization and I have regulators. So one of my regulators is, of course, the lattice spacing. So regularization means, and I have bare coupling constants that are put into the action, but these are, of course, not the physical coupling constants. So it's a standard logic. Then, when I approach a phase transition of, say, of second order, then, of course, in principle, of course, everything depends on my lattice scaling, and what I'm interested in extracting the asymptotic behavior of any observable, to leading order as I take A to 0, this lattice spacing. And of course, I will have typically to renormalize, say, additively or multiplicatively, say, my coupling constants as a function of this lattice cutoff. Yeah. And of course, some of them, they will just undergo infinite renormalization. I mean, but that is really the standard logic you would also apply, in any other lattice theory, or even, if you put, whatever, scalar field on the lattice or so.
Okay, I think I got it. Yeah, okay, thank you.
Okay, the next question is from Dmitry S. Dmitry, please tell us your name. Yes.
And show your face if you can.
And show your face if you can.
Hello.
Hi. Hi.
Yeah. Just ask 1 minute. What's the form of the equations? Don't see nothing new. In principle, the sum is written in Euclidean quantum gravity. As for me, this is trapping around the same formulas from quantum statistics, which different metrics. This is not quantum gravity. More precisely, the real equation are not written down.
What equations?
No, it is a mistake to quantize gravity because we must obtain a classical approximation from the from some quantum equations, and not so much in quantum from classical ones. Yeah, and in general, we don't need to talk about the quantization of gravity more precisely from the quantum space-time.
Yeah. So what is your question?
I'll be
maybe you can kindly, Dmitry, maybe you can kindly ask your question in chat, because I also don't understand what you ask for. Please ask your question in chat. And because the connection with you is not very good, the line you used is very bad. So please ask your question in chat, okay? Okay, very good. Thank you very much. Let's go to the next question. The next question is from Gaetana Fiore. Gaetana,
yes.
Are you here?
Yes, I can hear. Can you hear me?
Yes.
Yes.
Oh, nice picture. Yes.
Yes. Thank you for the nice talk. I would like to ask a few clarifications. First of all, you have obtained your results, and in particular, the emergence of this averaged tensor geometry starting from the action, putting in the path integral the action with, I mean, which you showed, so with a positive cosmological constant. Is it correct?
That's correct, yeah.
Yeah. Okay. In one of your slides, you were showing this Lorentzian triangulation. From the slide, I could see that you are kind of doing a slicing at a fixed T slicing, which is a global one. So you slice the whole.
Yes, yeah. So it's what I call global hyperbolicity in this discrete context. Yes.
So this is the basic. I mean, it is one essential ingredient of the construction, isn't it?
Well, there is a generalized way, but which doesn't have this strict time slicing. But yes, it's important that there is kind of a notion of time and causal structure.
Yeah, but you need to make a unique, I mean, global time slice to which you attach the vertices. Yeah,
that's convenient. It's not strictly necessary, as we showed in 1+1 and 2+1 dimensions. So you can have one where your slices are more, floating. I mean, there is not a strict time slicing, but you still have the light cones.
Yes.
All pointing in the same direction. Yeah.
Okay.
So it's not strictly necessary, but it's very convenient to do it like that. Mm-hmm.
Okay. Another thing I didn't catch is if this quantum Ricci curvature, this KQ which you introduced, classically, it only depends on the Ricci scalar or on the whole Ricci curvature.
Yeah, okay. So, you know, if I had more time, I would have shown it in more detail. So, in the classical theory, you can, of course, on the smooth manifold, you can Riemannian manifold, you can introduce local, let's say, normal coordinates. So you can compute for arbitrary metric, you can compute the sphere distance, and you can make an expansion in this delta parameter. So then you obtain to zeroth order, you obtain a constant that depends only on the dimension. Then at second order in delta squared, of course, that's what you expect on dimensional ground, you get the Ricci curvature and a combination of Ricci curvature and Ricci scalar curvature with specific coefficients. But of course, and then the higher order terms in principle.
So it depends not only on a Ricci curvature, not only through the Ricci scalar, but also with some other.
It's a genuine. I mean, you know what mathematicians call rich, RHC. I mean, so it's really the Ricci. I mean, the Rij, the Ricci curvature evaluated, you know, on a vector, on a direction, and to understand. To understand why it has a directional quality, you know, there's the double sphere.
Yes.
Of course, it has it has a direction to it. The relative location of the two spheres. So that's why it goes beyond. Very good question. Beyond scalar curvature, indeed.
Okay, very good. And this is the simplest averaged observables which involve this Ricci curvature, which you can build. There is no way, for instance, to translate in average terms the fact that the perimeter and the area, or let's say the surface and the volume of a sphere do not respect the law.
I understand. This correction. There are these classical correction formulas. So there are two things. So what I showed you is, of course, in answer to your previous question, the importance is that it's Ricci, not just scalar, but it's directional information.
Yes.
And there, well, this is the only prescription I know. If you are only interested in scalar curvature, you can do other things. You can indeed, and actually some of my students are currently looking at it in a very systematic way. If you're only interested in scalar curvature, there are many classical formulas which have kind of second order correction terms which know about curvature. So like the volume formula is a well-known example. You could use these two.
I see. Okay, thank you very much.
Okay, the next question is from Indrus Delfanic. Sorry for maybe my pronunciation is not correct. Indrus, please ask your question. Are you here? Okay.
Yeah, can you hear my question? My voice?
Yes.
Okay. First, I would like to also thanks for your talk and also for your quantum gravity course from PSI, which has helped me a lot. Which helped me a lot in understanding the quantum gravity things.
That's great to hear. Yeah, thank you.
Okay. So my question is that we know that in standard quantum field theory, there is consistency between the covariance formulations and also from the Hamiltonian formulations. And since this model, you mentioned before that it does not have a time emergence, does it mean that you cannot actually formulate it in terms of Hamiltonian formulations? And the second question is, I don't know whether you already discussed it or not because I entered late before. Why are you actually using the quantum curvature instead of just the standard holonomized curvature, as I understood from the lattice theory?
Okay. Let me start by the second question. So yeah, I didn't have time to cover all these things, but of course, people who know about Ricci curvature. So it's this Regge calculus. There, of course, it has a natural notion of curvature, which is deficit angles. Yeah, I guess that's what you mean, have in mind. So, and that's a notion of curvatures that people have used also in the quantum theory. Unfortunately, this curvature that in the continuum limit becomes infinite. So it's not useful as an observable. So you would say, okay, yeah, it has to be renormalized. That's true, but no one really knows how to renormalize it. So the deficit angle curvature seems perfectly fine on finite triangulations, but in the ensemble, so which is needed, of course, for the quantum theory, and where we take a continuum limit, that these building blocks all shrink to zero. Unfortunately, it's infinite, and therefore it's not useful. Yeah, so the other question you asked, about Hamiltonian versus covariant. Yeah, so yeah, very good. So of course, in principle, you start with the even relativistic field theory, right? You can, of course, always introduce a particular frame, and then you have a notion of time. Yeah, and with respect to that notion of time, you can then write down a Hamiltonian. Yeah, and of course, you should still remember that you can perform arbitrary Lorentz transformations, and of course, then the time will be a different one. So, but you can take care of this. So in gravity, the story in principle is similar. Of course, we don't have Lorentz transformations, but we have diffeomorphisms. So and there are many choices of time. But in principle, with any given time, there is, well, of course, it's more complicated because of constraints and diffeomorphism invariance. But in principle, a given notion of time has a given Hamiltonian associated with it. So in the framework I presented, so there is this, what comes with this lattice is also a notion of proper time, which a priori is not physical because it's just an element of the lattice. But what we have shown that because of these matching with these cosmological de Sitter shapes, we've shown that it is apparently proportional to cosmological time. So it has a physical notion. So in principle, we could, what ought to exist in our framework is a Hamiltonian that's kind of conjugate to this notion of time. And in 2 dimensions, so in 1+1, where everything can be just solved analytically, yeah, this is exactly what one can construct. If one takes this time seriously as a notion of time, there is an associated Hamiltonian, which can be, it's a quantum mechanical Hamiltonian, but it can be explicitly written down. Its spectrum is known. So as a matter of principle, yeah, even if you have a covariant formulation, whenever with any given notion of time, and I would say you should, of course, make sure that this notion of time has some kind of physical meaning. But of course, it's tricky, in quantum gravity. But for instance, if you have what cosmological time is, I would say is one of the most physical notion of times. And you imagine you have an initial singularity, and cosmological time, one way of thinking of a cosmological time is just you let all your geodesics run forward, and it defines, a notion of time in the sense of distance from the initial singularity. So I would say in something like this, apparently one has naturally here in the CDT formulation also.
Okay. The next question, it comes from Norma Sanchez. Norma, please ask your question. Are you here?
Yes. Yes.
Okay.
Thank you very much. Good afternoon. I have some points, brief points, and one question, please. So the first is about boundary conditions in your path integral. Doing these triangulations, you have already chosen, I assume, a boundary condition, a physical boundary condition for the path integral. Yes. It's implicit there.
Yes, well, I mentioned it in passing, but I don't blame you if you don't remember it. It's our spatial slice. I mean, in most of the analysis is three-dimensional spheres, and the time direction we typically, but for basically to make our life simpler, we cyclically identify. So,
yes,
the topology we put in is S3 cross S1 typically.
So these triangulations, as you said at the beginning, you said it's unique, it gives you a unique theory, but I mean, is something, I mean, perhaps more elaborated than a model with discrete geometry, because it's a kind of discretization too.
I didn't understand the question. So
no, it's a comment. It's a comment about doing triangulations and doing discrete lattice. I mean,
no, but we're taking continuum limit. We are not interested in the finite structures.
You put by hand in some sense, choosing the triangulation, a regulator. I mean, the theory is finite because you have put it a regularization.
Yeah, but it's not finite as I remove this regulator, of course. That's why I have to renormalize in principle, you know.
Yes,
it's a standard logic of QFT on a lattice.
Yes, it's doing QFT in a lattice.
Yeah, but it's taken the continuum limit, of course, and that's why I insisted. One has to, of course, understand one needs second-order transitions in this underlying statistical model, and in order to define a continuum theory, one has to understand what happens as one approaches these critical points.
The critical points. Okay.
Yeah, of course, and one doesn't take seriously, you know, these discrete measurements. One makes a kind of finite size scaling analysis.
I see.
So you don't take these literally, then it's just any discrete model. No, you look for scaling behavior.
You do as in critical, I mean, as in critical,
yes, of course.
QFT, I mean, and universality classes and so on.
Exactly. So that is a lot in 2 dimensions.
I understand. Yes. Now, why then, or perhaps as a consequence, when you find, as I said, a quantum curvature, you have only a positive curvature, and not as an emergent. You see, the emergent positive curvature, and not a negative curvature, for instance. I mean, you could. I imagine that you could have the 2 possibilities, and one for describing one kind of set of vacuum, and the other hand for describing, for instance, the zeta and so on. I don't see why you have only positive curvature in the emergent.
Yeah, but Norma, it's a finding. It's, well, I would say I'm not putting it in by hand. This is an outcome.
Yes, but it's an outcome which I do not understand why in the outcome there are no possibility for the negative curvature. I mean, one thing is one find a result. The other thing is one want to understand why this result physically. Because the saying that this then can be applied to universe and early universe, that is another thing. I mean, I want to see why the positive curvature, only positive curvature, emerge from this framework, and not and perhaps changing something. You could also find as an output the possibility of negative curvature. It seems to me, because always when we find this kind of geometries saying constant curvature, saying we have the two signs.
Yeah, okay. I have various, so you're asking very interesting question. I have various pieces of answer. So number one, you know, in an earlier question, you asked about topology. And of course, one should wonder in terms of boundary conditions, does a certain choice, does that bias the outcome? Okay.
Yeah, and that is what I am pointing. Yes.
Yeah. No, but yeah. So the following is the case. So you're putting in cylindrical geometries, right? However, the dynamics of the system drives it to a topology which is an S4. It's a dynamical effect.
Yeah, because you put.
No, but it's not, I'm not putting in the sphere. I'm putting in a cylinder. And what I'm saying is dynamically, this system is driven by this non-perturbative dynamics in such a way that it wants to be a sphere, an S4. Okay.
Yeah.
So I insist this is a dynamical thing. So what it tells you in a way is that some of the boundary conditions you're putting in can be overridden by the dynamics of the system, right?
Well,
that is so
the boundary conditions. The boundary conditions are doing the show.
No, not
of course,
necessarily.
The dynamics. But if you
I just told you. I'm putting in one topology, and dynamically the system tells me it wants to have another topology.
Yeah.
Okay,
I would like
opposite.
To see. Yeah,
that is
I
opposite
like
to what you say.
Yeah,
and number two,
I would like to see, for instance, which is how to obtain another result than the sphere. A negative curvature. A negative curvature.
Well, let me make one other. Yeah, stop. Let me make one other comment, which is so at the level of bare coupling constants. The cosmological bare coupling constant one has to put in all of these random geometry models is positive. Okay, so we're talking about lambda.
Yeah.
Otherwise, the models don't exist. So, but of course, what is relevant is the sign of the renormalized lambda. This also comes out from how the renormalization of these models work. It will always. It's not. It's a free parameter, but it's always. It has to be positive.
I see. So
you can say, well, but I want also a negative one. Well, this and none of these formalisms will give it to you because they are not defined. Whether that tells us something deep about nature or in your view is just a failure of the formalism. Well, that's the way it is.
Yeah. So I think that in quantum gravity, a negative curvature is also possible for some situations. Otherwise, but but
it's
a matter too.
No. Look, but this is absolutely not excluded. What I'm saying is that the ground state. No, the ground state and the vacuum. Yeah. This is what I'm presenting you is the absolute vacuum, and it has this property apparently.
Of course, this is what I am saying. Yes, yes.
If it clashes with your expectations,
I see.
Then that's it.
And now, yes,
but you're making very good points.
Thank you. Yes, I understand. I hope I try to understand. So, the two short points I have is one is one perhaps more involved than the other more simpler. And one is you talk about the spectral dimension and even fractal property. So it seems to me that describing in this way the geometry, this is a fractal. This could have as an output a fractal dimension.
You mean in four
fractal
dimensions?
description, a quantum geometry, which have, you know, so high fluctuations, or could have a fractal description.
Well, I would say, I mean, of course, fractal is a very,
I mean, the dimension,
it's a very vague notion. So I would say,
no, fractal is mathematically is a very well-defined notion.
Yeah, but the way
Mandelbrot definitions. I mean,
fine, yeah, but the way, sorry, I didn't know the way you're using it. I mean, sometimes it's used in a very hand-waving manner in people working in quantum gravity. So, of course, if you're saying we define it as self-similarity, yeah.
Yes, then, I talk about fractal in a very precise way, which is self-similarity, fractal dimension, computation even of the amplitude.
No, I mean, so the geometries in 4 dimensions here, they're not fractal. And I can tell you why they're not fractal.
But in 2 dimensions, in 2 dimensions
they are. But why can they be that? Because there is only a single scale in 2 dimensions, right? Which is lambda or h bar. It's all the same. There's only a single scale. And indeed, you know, the geometries of Liouville gravity, they are genuine fractals in the sense of self-similarity. They have funny properties. They have Hausdorff dimension 4. They have spectral dimension 2. So they're very, very, very non-classical. You know, even in this limit, you know, this maybe, which I mentioned, the Brownian sphere, is this mathematical limit that people study. However, of course, in 4 dimensions, you have more than, I mean, you have several scales associated with dimension for constants. So at the very least, you have a small scale, kind of h bar scale, right? And G Newton. And then you have, of course, lambda at the large scale. So if your theory was fractal or self-similar, I don't think it would be a good theory of quantum gravity. But of course, it has fractal aspects, you know.
No, it have. I think a good theory of quantum gravity have fractal aspects.
That's right.
Asymptotically, or I mean, a fractal is not the fractal, not in an infinite domain, but in a finite domain. And that is what one observes too in many realistic systems.
Yeah, so I think one scenario that people also, I mean, mention is, you know, when we come to the Planck scale, you know, it's always a question, what is the ultraviolet completion? Well, it could be that it doesn't make any sense to go to smaller than the Planck scale because it's fractal. So you know, although you can zoom in and you can ask, you know, what happens at smaller and smaller scales, things will just reproduce themselves.
The last point is, I mean, it's a more simple one. How deep do you go in the quantum gravity domain in Planck units set?
Yeah. Yes.
How a number, please.
Yeah,
For instance,
yes.
this.
Yeah. So these blobs I showed you. So they are in the range of, I mean, the volumes we can simulate. They are about up to 1 million building blocks, and the ranges of bare coupling constants. So the part of phases you can explore, they are on the order of 20 Planck lengths in linear diameter.
So it's not too far in some sense.
Yeah, it's not too far.
It's not too far.
Yeah,
it's not in the deep set, what I call the deep quantum gravity domain. I mean the transplanckian, because
it's not transplanckian. No, so our lattice spacing. So we cannot resolve L Planck, but we can resolve maybe, you know, 3 or 4 L Planck. That is the best we can do.
Because the truly, I mean, and the very interesting quantum gravity domain is transplanckian. I mean, the onset of quantum gravity is Planckian, is Planck scale, and we need to go beyond that to really.
I mean,
in the.
But what we do see,
we know that in the early universe, Planckian time it's just, I mean, we cannot go till zero because of quantum fluctuation, but we will go to a fraction and fraction of Planckian time, and it still is quantum gravity, is trans-Planckian, and
well, I don't know how far you want to go. We have a window between like 2 and 20 Planck lengths, and we see a very, very strongly quantum fluctuating system that clearly is not describable classically, but marvelously, even in this within 20 Planck lengths, there are some observables which, in the sense of expectation values, already display recognizably classical aspects.
Yes, but
it's a limited window, but I would say it's very important because, you know, we don't have much access to this regime otherwise.
Yeah, for me, is the truly quantum gravity is beyond Planck scale, beyond in the sense of a smaller scale, because it's quantum Planck scale is the onset of quantum gravity.
We don't know. These are just dimensional
arguments. That is what appears. I mean, from the what we know. I mean, with inflation and black holes and black holes too.
Well, I don't know, but here I'm giving you another set of arguments, and I'm just presenting, you know, my findings. So if they contradict your knowledge, then that's so.
Well, but it's not contradictory, but it could be what I'm saying. It's not contradictory, but complementary to go beyond this.
Yeah, but you know, we don't have direct means of really studying, you know, these systems in the way we're doing it. Is, you know, we have a scale window. And
yes, no, but I am not saying with triangulations and this approach. I am saying with others approach of quantum geometry.
No, that's great. I'm looking forward to these results. Yeah. If there are, you know, if there are ways to simulate at even smaller scales, I mean, I don't know how to do it.
Yes, there are ways. I mean, in which starting. I mean, not doing triangulations or starting from this lattice, or I mean, in analogy with QCD, but finding the discreteness, the discrete level of space-time from the theory of a more quantum extension, from the quantum extension to Planck scales. I mean, here, I mean, the quantum principles extended to the Planck domain.
So how would you do it? How would you do that?
A classical quantum or wave particle duality extended to the Planck, extending beyond the Planck scale, for instance.
Yeah, but it's very difficult, as you know, to.
No, but I mean, I invite you to consult my trilogy in 2019, which is published, and my last physical review, 2021, and in which you can find, I mean, a summary, and in which the discrete levels of the space-time are found, and for the universe.
And you can also compute like observables and such things.
Yes, you can compute observables. You can find the limit. You can do for the universe, and you can do for black holes, and you can find the continuous limit of the space-time. I am not using a path integral approach, but very interestingly, the path integral results, for instance, from Gibbons and Hawking, which started the Euclidean path integral and so on, and the entropy are found as particular case of this.
But I mean, this would be, I mean, typical, I mean, semi-classical path integrals then, right?
the semi-classical path integral when you find, when you
look for several points.
The saddle point of the Euclidean path integral is the gravitational entropy, which is a semi-classical, the Hawking or Bekenstein is a semi-classical entropy, but with extension of the classical quantum duality for gravity, which is classical quantum gravity duality, you find also all the extension of the partition function, entropy, temperature to the Planckian and transplanckian domain.
Yeah, that's very good. I would say it's complementary, of course. My path integral is really fully non-perturbative. Yeah.
It's a non-perturbative, but no, it's a non-perturbative approach.
I understand, but here my path is different. But here my path integral is non-perturbative. But you have duality. You're bringing duality, and that's fine. That's another approach.
As I am saying, it's another approach, and it's a duality which is a general one, which is the foundational duality for quantum mechanics, which is the wave-particle duality.
Yeah, good.
So I do not, with this I finish, and that so you will see, I do not start from general relativity or a gravity theory to quantize it, but I start from quantum theory and extend on the foundation of quantum theory as this principle I mentioned, and then, which is it's not ad hoc, because classical quantum duality is something which is completely real, and I extend to Planck and then to gravity set, and then it appears clearly that is Planckian and transplanckian.
Yeah, thanks.
Because new duality appears, and it's very, and it works for the universe, and it works for black holes.
Norma, could you please send very precise reference to this your paper? Yes, to in chat, because some people can be.
Anyway, thank you for your good comments, and
thank you.
Thank you.
Thank you
Thank you very much.
Very interesting.
Thank you to you.
It's left two questions. The first of which these two questions is from Gabriel Gionti. Please, Gabriel, ask your question. I hear.
Yeah, thank you, Renata, for this, your talk. And I have one brief question, maybe something I did not understand. You were saying that you are computing the observable using the Riemannian path integral, or no? I was wrong.
Yeah. So I'm starting with a Lorentzian path integral.
Okay.
So there, it just so happened on these piecewise flat geometries, there's one parameter I can analytically continue. I mean, really completely rigorously in the complex plane.
You are in the case you are in the case in which you can do this.
Yes, I mean, this is not possible in the continuum.
In the continuum.
But these special piecewise flat geometries have a well-defined Wick rotation. So this is kind of unique, exactly. And then I do everything. Yeah, I do all the computation in the Riemannian domain, indeed. Yeah.
Okay, that's it. Thank you.
Okay, let's go to the next question. It is from Ariel Vini-Epoye. I'm not sure that my pronunciation is correct, but in any case, Ariel, could you please ask your question? As I understand, you already wrote the question in the chat. So would you please tell us your question?
Yes, sure. Thank you for this amazing lecture. And my question is, do we already have a track for the proof of the existence of the graviton? And if this particle exists, will it be compatible with the Schrödinger equation or the Dirac version of Schrödinger equation?
Yeah, no, we don't have any direct proof of the existence of gravitons. And of course, you probably know there is some discussion to what extent a graviton can be a kind of a physically, kind of like a real quantity, in the sense of, are we able to set up a gravitational analog, something like of the photoelectric effect, something that would really, in that sense, prove the particle property. So I think people have, of course, thought about this and made kind of Gedanken experiments. And when you try and do this, typically it turns out that the detectors you would need to observe this are so big that they would collapse under their own gravitational, attraction and form a black hole. So it's unclear. I would say the existence of gravitons, I would say, is not necessarily the same as saying, does a theory of quantum gravity exists? Because there may be other phenomena that people are studying which would, nail down that gravity is indeed a quantum theory. For example, by, this is these tabletop experiments where people currently are trying to look for entanglement effects and, just demonstrate the quantum nature, which would be, fine. And well, it hasn't been shown yet, but it would be perfectly fine to do it this way without there ever being gravitons detected or even detectable. So I think these are in principle two different questions.
Okay. Okay, we have a lot of questions. Maybe I will ask a very last question, very short one, but very technical.
Yes.
Because you spoke about the reduction. You said that starting from 4-dimensional case, you got 2-dimensional question. My question is very simple. If you got Lorentzian 2-dimensional case or Euclidean?
Well, well, I would say in principle, questions about dimensionality are probably pre-geometric. Right? So I would imagine that although, of course, we are extracting this from a spectral, in a Wick-rotated framework, I would expect, that it is independent of the signature, ultimately.
Okay, thank you. So I would like to say that you are a champion in the number of questions. By the way, I see one more question.
Alex has another question.
Alexei Koshelev. Alexei, do you still want to ask your question, or you have to tell us some information? Alexei?
No, I really got a question.
Yes, please.
Over the discussion. So first of all, thank you very much for a lot of very interesting information during the talk. You see, I am a bit confused. You many times repeated that you have Lorentzian signature and then you analytically continue to Euclidean signature. But why at all you have to consider Lorentzian or Euclidean? Why don't you average over all possible metrics which can appear?
Well,
actually, what tells you that some signature is fixed before you start?
Well, ultimately, there is very little, especially when we're talking about theories of dynamical geometry. However, I would say I'm just following, by starting out in a Lorentzian path integral, I would say I just follow the standard recipe of quantum field theory. I'm looking at the classical set configuration space, right? And yeah, well, and then there is a computation I want to do, which is the Lorentzian path integral. Okay, of course, then I cannot do it in 4 dimensions, so I have to resort to analytic continuation in order to be able to do the integral. And then in the end, I will rotate back. So all of this is standard quantum field theory. Now you're saying, but hang on, I want to enlarge my configuration space. I want to add many, many more things. Yeah, well, that might be possible. I don't know. It might be conceptually difficult or interesting. Just go ahead and do it. Just go ahead and do it. With me, I would say is Occam's razor. I'm using kind of the minimal set, which I think is the relevant degrees of freedom, right? And if I use Lorentzian and Euclidean, well, this is a vast enlargement of the classical configuration space. Yeah.
No, you see, when you speak about canonical field series, and I understand, then you just put some field theory of some scalar, or I don't know, fermion or some, or in some background, and you are happy to live in this background. But here, you are on the way to determine your background, and according at least to ideology of Feynman, as far as I understood it, you have to average over all possible configurations of your fields. And since your field is metric, it is not limited to be just -1 +++ signature in 4 dimensions or something like this. It can be any. And conceptually, I just don't understand in this particular case of gravity, why do you narrow your space? And I understand that it will be much more complicated. I understand that it's
okay.
But the question is, don't you lose anything on the way?
Well, I would say, look, Feynman doesn't tell us at all what configuration should go in the gravitational version of his sparse integral. He doesn't. Okay, you could say, look, I should sum over everything of every dimension, you know, and every this and every that. You're making your life very hard. Number one, you must be careful if you have a large configuration space, you are not able to do the sum, and it will just be infinite, and you will not even be able to renormalize it. But I have a more precise answer to your question. We already know that even the Euclidean spaces alone give you a nonsensical result. They never lead to extended geometry. So now you want me to include Euclidean on top of my Lorentzian ones. We already know that of the Euclidean ones, there are many, many more. So they will overwhelm this combined path integral, and the result will be that of the Euclidean path integral, very likely. And this has already been shown to not lead to very interesting results. So that's a more specific answer to your question. You see, on a priori grounds, there is no way to argue this is the right configuration space or this other is the right configuration space. I mean, of course, you must make sure that it's not too few things. So you still need, of course, local degrees of freedom, but you should also be worried it shouldn't be too many things, because then you are not able to do the path integral, you know, and we normalize it by standard methods. So there is some, you know, there is a range in between, but in there, you don't know what the right answer is. So in a sense, you know, what we've shown is imposing this causal structure seems to be very important to get out a good classical limit. If you tomorrow come with a different configuration space that is totally different and maybe larger and also gives interesting results, I would say, well, that's great, you know, but it's difficult to argue a priori. It doesn't seem possible.
Okay, I see. Yes, thanks. No, actually, I was wondering about consistency of this. So you arguing that by getting good results, you believe it is a consistent, let's say, truncation of possible configurations?
It's not a truncation. It's just one choice.
I see.
Of configurations for which I then evaluate the path integral. But really, there is nothing, and the outcome is, of course, well, of course, we cannot control this analytically. So the outcome is just to say, look, here is evidence of, you know, higher order phase transition. Here's evidence of this de Sitter, blah, blah, you know. But this is as good as it gets. Of course, really, if you have an alternative way of doing the path integral, I think a priori, it might be as good. But of course, we have real trouble finding any interesting results. So, you know, for the time being, my question is not, how could I generalize my model in 100 different ways? Rather, look, I'm seeing some interesting things. How do I understand more complete information within this model? And I'm also relying on some kind of universality, you know, that there are not zillions of quantum gravity theories out there, you know, with, of course, you know, you may discover by your alternative definitions, probably if this makes sense, there are probably many ways to get to this theory, and you may make another choice maybe of initial configuration space, but the universal properties then are hopefully could be still very similar to what I find, you see. So I think there's some save, you know, something can save us also from, you know, a universe with many possibilities and many free parameters. And, you know, of course, if the world is like this, then we will never find a predictive quantum gravity theory.
I see. Okay, thank you very much.
Okay, I think that maybe now we have to stop. In fact, so it was 1.5 hours of discussion. So, Renata, thank you very much.
It's my great pleasure.
Excellent talk and
Thank you very much.
discussion.
Thank you very much.
Yes,
Thank you for all the good questions.
Asking questions, yes.
Yes.
So please don't forget to send your transparencies.
Okay, I will do that.
Thank you. Goodbye.
Okay, you can send to me, Renata. Yes.
Bye-bye.
Okay.
Bye.
Very good.
Bye.
Very good seeing everyone. Ira, very nice seeing you.
Yeah.
Yes, nice to see you.
Thanks for the good questions.
Bye-bye.
Bye.
Bye.
Bye. Bye, Norma.
Okay.